At the bottom of our world lies a continent so vast and mysterious that it continues to challenge our understanding of Earth itself. Antarctica, larger than Europe and Australia combined, holds within its frozen expanse 90% of the world's fresh water and serves as a natural laboratory for some of humanity's most important scientific discoveries. This ice-covered landmass, roughly 14 million square kilometers in area, represents the last great frontier on our planet, a place where ancient history lies preserved in ice and where the future of our climate may be written. The sheer scale of Antarctica defies easy comprehension. To put its size in perspective, the continent is nearly twice as large as Australia, encompassing an area greater than the United States and Mexico combined. The ice sheet that covers this massive landmass averages over 2 kilometers thick, with some regions reaching depths of more than 4.8 kilometers. If this ice were to melt completely, global sea levels would rise by approximately 60 meters, fundamentally reshaping every coastline on Earth. Antarctica's geography is as diverse as it is extreme. The continent is divided by the Transantarctic Mountains into two distinct regions: East Antarctica, which contains the bulk of the ice sheet and sits primarily on bedrock above sea level, and West Antarctica, where much of the ice rests on bedrock below sea level. This geological distinction has profound implications for ice stability and future sea level rise, as West Antarctic ice is more vulnerable to warming ocean temperatures. The continent's coastline stretches for over 17,000 kilometers, much of it consisting of massive ice shelves that extend far into the Southern Ocean. These floating ice platforms, some as large as entire countries, serve as crucial barriers that slow the flow of land ice into the ocean. The Ross Ice Shelf alone covers an area roughly the size of France, while the Rhone-Filchner Ice Shelf rivals the combined area of Germany and Austria. Beneath the ice lies a landscape that would be unrecognizable to most people's conception of Antarctica. Advanced radar and satellite technology have revealed vast mountain ranges, deep valleys, and even what appear to be ancient river systems carved into the bedrock. The Gamburtsev mountain range, buried under more than 3 kilometers of ice in East Antarctica, rivals the Alps in height and complexity, yet it remains completely hidden from surface view. The climate of Antarctica represents one of Earth's most extreme environments. Perhaps most remarkably, Antarctica receives less precipitation than many of the world's deserts. The interior of the continent qualifies as a polar desert, with annual precipitation equivalent to less than 200 millimeters of rain. This extreme dryness, combined with fierce winds and bitter cold, creates conditions that preserve organic matter for thousands or even millions of years, making Antarctica an unparalleled archive of Earth's history. The isolation of Antarctica has created unique ecosystems that exist nowhere else on Earth. While much of the continent appears lifeless, microscopic organisms thrive in surprising places. Bacteria have been found living in rocks, under glaciers, and in lakes that have been sealed beneath ice for millions of years. These extremophile organisms provide valuable insights into the limits of life on Earth and offer clues about the possibility of life on other planets with similarly harsh conditions. Marine ecosystems surrounding Antarctica are among the most productive on the planet during the brief summer season. The Southern Ocean teems with krill, small shrimp-like creatures that form the foundation of an extensive food web supporting whales, seals, penguins, and countless species of fish and seabirds. Emperor penguins, the largest of all penguin species, have evolved remarkable adaptations to survive the Antarctic winter, including the ability to dive to depths exceeding 500 meters while holding their breath for more than 20 minutes. The magnetic and atmospheric properties of Antarctica make it an ideal location for certain types of scientific research impossible to conduct elsewhere. The continent's position at the magnetic South Pole creates unique conditions for studying the Earth's magnetic field and its interactions with solar radiation. The aurora australis, or southern lights, provide spectacular displays of these electromagnetic phenomena, offering scientists direct observation of processes occurring in the upper atmosphere. Antarctica's pristine environment also makes it invaluable for astronomical research. The combination of high altitude, extremely dry air, minimal light pollution, and months of continuous darkness during winter create some of the best observing conditions on Earth. The South Pole Telescope and other installations have made groundbreaking discoveries about the cosmic microwave background radiation and the fundamental structure of the universe. The logistical challenges of conducting research in Antarctica cannot be overstated. Every piece of equipment, every gallon of fuel, and every morsel of food must be transported thousands of kilometers across some of the world's most dangerous waters. Research stations must be designed to withstand extreme weather conditions while providing life support for scientists and support staff during months of isolation. The cost of maintaining a year-round presence in Antarctica runs into billions of dollars annually across all participating nations. Despite these challenges, Antarctica continues to attract researchers from around the world because of its unique value as a natural laboratory. Ice cores drilled from the continental ice sheet provide detailed records of Earth's climate extending back over 800,000 years, offering crucial data for understanding both natural climate variability and human-induced climate change. Subglacial lakes discovered beneath the ice sheet harbor ecosystems that have been isolated from the surface world for millions of years, potentially preserving ancient forms of life and providing analogies for extraterrestrial environments. As we face global challenges related to climate change, biodiversity loss, and resource management, Antarctica's role as a scientific research platform becomes increasingly important. The continent serves as an early warning system for global environmental changes, a testing ground for technologies that might one day be used in space exploration, and a reminder of the planet's capacity for both resilience and fragility in the face of changing conditions. The Antarctica we know today, a land of endless ice and bitter cold, represents just the latest chapter in a geological story spanning hundreds of millions of years. Beneath the frozen wasteland lies evidence of a dramatically different world, one that challenges our understanding of Earth's climate history and offers profound insights into the planet's capacity for change. Scientific evidence accumulated over decades of research reveals that Antarctica was once part of the supercontinent Gondwana, positioned much closer to the equator. Fossil discoveries across the continent tell the story of lush forests, flowing rivers, and diverse ecosystems that thrived in temperate and even subtropical conditions. These findings force us to reconsider not only Antarctica's past, but also the dynamic nature of Earth's climate system and the potential for dramatic environmental change. The most striking evidence of Antarctica's ancient warmth comes from fossilized plant remains found throughout the continent. In the Beardmore Glacier region, just 500 kilometers from the South Pole, members of Robert Falcon Scott's ill-fated 1912 expedition discovered fossil leaves that initially puzzled scientists. Later analysis confirmed these belonged to Glossopteris, a genus of seed ferns that dominated southern hemisphere forests during the Permian period, roughly 250 to 300 million years ago. The presence of these fossils so close to the current South Pole provided early evidence that Antarctica had not always been frozen. More recent discoveries have painted an even more detailed picture of ancient Antarctic ecosystems. Paleontologists have uncovered fossilized trees still standing upright in their original growth positions, preserved in sandstone formations on Alexander Island and elsewhere along the Antarctic Peninsula. Some of these petrified giants reach heights of 7 meters, suggesting they grew in forest environments with favorable conditions over extended periods. Chemical analysis of fossil wood reveals growth rings, similar to those found in trees from temperate climates, indicating seasonal variations in temperature and precipitation that supported sustained forest growth. Perhaps the most remarkable window into Antarctica's prehistoric climate comes from discoveries made in recent decades using advanced drilling and analysis techniques. Sediment cores extracted from beneath ice sheets and from offshore marine deposits contain microscopic fossils, pollen grains, and chemical signatures that reveal detailed information about past environmental conditions. These records show that parts of Antarctica remained ice-free and supported vegetation as recently as 15 million years ago, much more recently than previously thought possible. During the Eocene epoch, approximately 50 million years ago, global temperatures were significantly warmer than today, and Antarctica experienced what scientists call a greenhouse climate. Fossil evidence from this period includes remains of palm trees, baobab trees, and other warm climate vegetation. Marine fossils from the same era reveal that ocean temperatures around Antarctica were warm enough to support tropical and subtropical marine life, including early whales and diverse fish communities that would be unable to survive in today's frigid Southern Ocean. The transition from this ancient greenhouse world to the ice-covered continent we know today was neither sudden nor simple. Ice sheet formation in Antarctica began approximately 34 million years ago during a period known as the Eocene-Oligocene transition. This dramatic climate shift was triggered by multiple factors, including changes in atmospheric carbon dioxide concentrations, the gradual separation of Antarctica from other continents due to continental drift, and the establishment of the circumpolar current that isolated Antarctica from warmer ocean waters. The formation of the Antarctic circumpolar current represents one of the most significant oceanographic changes in Earth's history. As the Drake Passage opened between South America and Antarctica, and the Tasmanian Gateway separated Antarctica from Australia, a massive circular current system developed around the continent. This current acts as a thermal barrier, preventing warmer waters from northern oceans from reaching Antarctic shores and contributing to the continent's thermal isolation. The growth of the Antarctic ice sheet was not a steady process, but occurred in stages, with periods of ice advance and retreat corresponding to global climate fluctuations. During warmer interglacial periods, the ice sheet shrank significantly, allowing tundra and limited forest vegetation to return to coastal regions. Evidence from the Pliocene epoch, approximately 3 to 5 million years ago, suggests that global sea levels were 10 to 25 meters higher than today, largely due to reduced ice volume in both Antarctica and Greenland. One of the most intriguing aspects of Antarctica's climate history involves the discovery of fossilized remains in the McMurdo Dry Valleys, one of the most extreme desert environments on Earth today. These valleys, which receive virtually no precipitation and experience some of the harshest conditions on the planet, contain fossils of mosses, lichens, and other organisms that lived there when conditions were more favorable. The preservation of these organic remains in such an arid environment provides unique insights into how ecosystems respond to extreme climate change. Recent research has also revealed that Antarctica's ice sheet has been more dynamic than previously understood. Rather than forming once and remaining stable, the ice sheet has undergone numerous cycles of growth and retreat. During the warmest periods of the Pliocene, parts of the West Antarctic ice sheet may have collapsed entirely, contributing to significantly higher global sea levels. This finding has important implications for understanding how Antarctic ice might respond to current and projected future warming. The study of Antarctica ancient climate relies heavily on proxy data, indirect evidence of past conditions preserved in rocks, fossils, and ice. Oxygen isotope ratios in fossilized marine organisms provide information about past ocean temperatures and ice volume. Leaf fossils reveal details about atmospheric carbon dioxide concentrations and seasonal temperature variations. Volcanic ash layers help scientists establish precise chronologies for environmental changes. Perhaps most remarkably, some of the best preserved evidence of Antarctica's ancient environments comes from the continent's unique preservation conditions. The extreme cold and dryness of modern Antarctica act as a natural freezer, preserving organic material that would have long since decomposed in more temperate climates. Mummified seal carcasses found in the McMurdo dry valleys have been dated to several thousand years old, while bacterial communities in permanently frozen soil may preserve genetic material from much earlier periods. These discoveries about Antarctica's past climate have profound implications for understanding current climate change and predicting future environmental conditions. They demonstrate that Earth's climate system is capable of dramatic reorganization over geological timescales, and that even the most seemingly permanent features of our planet, like the Antarctic ice sheet, are actually dynamic components of a continuously evolving system. The transition from the warm, forested Antarctica of the distant past to today as ice-covered continent represents one of the most dramatic climate changes in Earth's history. Understanding this transformation provides crucial context for evaluating current environmental changes and helps scientists develop more accurate models of how ice sheets, ocean currents, and global climate systems might respond to ongoing warming trends. The modern era of Antarctic research has revolutionized our understanding of life on Earth, climate systems, and even the possibilities for life beyond our planet. Through advanced technology and international cooperation, scientists have uncovered remarkable discoveries that challenge fundamental assumptions about the limits of life and the interconnectedness of global environmental systems. One of the most significant breakthroughs in Antarctic research came with the discovery and exploration of subglacial lakes, bodies of liquid water that exist beneath kilometers of ice. Lake Vostok, the largest known subglacial lake, was first identified through radar surveys in the 1970s, but was not directly accessed until 2012. This massive freshwater lake, roughly the size of Lake Ontario, has been sealed beneath the East Antarctic ice sheet for an estimated 15 to 25 million years, creating one of the most isolated environments on Earth. The exploration of Lake Vostok and other subglacial lakes has yielded extraordinary insights into extremophile organisms, life forms that thrive in conditions previously thought to be uninhabitable. When Russian scientists finally penetrated the lake's surface after decades of careful drilling, they discovered a thriving ecosystem of bacteria and other microorganisms that have evolved in complete isolation from the surface world. These organisms survive in perpetual darkness, near freezing temperatures, and under immense pressure, deriving energy from chemical processes rather than photosynthesis. The implications of these discoveries extend far beyond Antarctica. The conditions in subglacial lakes closely resemble those believed to exist beneath the ice-covered surfaces of Jupiter's moon Europa and Saturn's moon Enceladus. If life can thrive in Antarctica's subglacial environment, it suggests that similar organisms might exist in the subsurface oceans of these distant worlds. This connection has made Antarctic research a crucial component of astrobiology, the study of potential life beyond Earth. More than 400 subglacial lakes have now been identified across Antarctica, connected by an extensive network of subglacial rivers and streams. This hidden hydrological system, completely separate from surface water bodies, represents one of the largest freshwater systems on Earth. The flow of water through this network influences ice sheet dynamics, affecting how glaciers move and respond to climate change. Understanding these processes is crucial for predicting future ice sheet behavior and sea level rise. Another groundbreaking area of Antarctic research involves the extraction and analysis of ice cores, cylindrical samples of ice that preserve detailed records of past climate conditions. The ice that accumulates on Antarctica's surface contains trapped air bubbles, dust particles, and chemical signatures that provide direct evidence of atmospheric conditions extending back hundreds of thousands of years. The longest ice core records from Antarctica reach back approximately 800,000 years, offering an unparalleled archive of Earth's climate history. Ice core analysis has revealed crucial information about natural climate variability, volcanic eruptions, atmospheric pollution, and the relationship between greenhouse gas concentrations and global temperatures. These records show that atmospheric carbon dioxide levels have fluctuated naturally between approximately 180 and 300 parts per million over the past several 100,000 years, but current levels, exceeding 420 parts per million, are higher than at any time in the ice core record. The precision of ice core dating allows scientists to correlate Antarctic climate records with events from other parts of the world, revealing the global interconnectedness of climate systems. For example, ice cores show evidence of volcanic eruptions from distant locations, such as the massive Tambora eruption in Indonesia in 1815. Demonstrating how atmospheric circulation patterns distribute particles around the globe within months of major events. Antarctic research has also led to the discovery of unique geological phenomena that exist nowhere else on Earth. Bloodfalls, a striking red waterfall that flows from the Taylor Glacier in the McMurdo Dry Valleys, initially puzzled scientists who couldn't explain the vivid coloration. Research revealed that the red color comes from iron-rich water originating from a subglacial pool that has been isolated for over 1 million years. When this water reaches the surface and contacts oxygen, the dissolved iron oxidizes, creating the dramatic red coloration. The microbial ecosystem in the Bloodfall's source water represents another example of extremophile life, with organisms that derive energy from iron and sulfur compounds in the absence of light and oxygen. These chemosynthetic bacteria provide insights into how life might survive in similarly extreme environments on other planets or in Earth's deep subsurface. Marine research around Antarctica has revealed ecosystems of extraordinary diversity and productivity. Despite the harsh conditions, the Southern Ocean supports some of the most abundant marine life on Earth during the brief summer season. Antarctic krill, small shrimp-like crustaceans, form massive swarms that can be seen from space and serve as the foundation for complex food webs supporting whales, seals, penguins, and countless other species. Recent discoveries beneath Antarctic ice shelves have revealed thriving communities of organisms living in perpetual darkness, sustained by nutrients transported by ocean currents from distant locations. In 2021, researchers drilling through the Filchner-Ronne ice shelf discovered stationary organisms, including sponges and other filter feeders, living on a boulder more than 260 kilometers from the nearest source of sunlight. These discoveries challenge assumptions about the limits of life in extreme environments and demonstrate the connectivity of ocean ecosystems even in the most remote locations. Technological advances have revolutionized Antarctic research capabilities. Autonomous underwater vehicles can now explore beneath ice shelves in areas too dangerous for human divers, while satellite technology provides continuous monitoring of ice sheet changes, wildlife populations, and weather patterns. Ice-penetrating radar allows scientists to map subglacial topography and water bodies without physically accessing them, while sophisticated drilling equipment can extract samples from previously inaccessible locations. The study of Antarctic meteorites represents another unique research opportunity. The continent's ice sheets act as a natural collection system, concentrating meteorites that fall over vast areas and preserving them in excellent condition. Some Antarctic meteorites have been identified as originating from Mars, providing direct samples of material from another planet. The pristine preservation conditions allow detailed analysis of these extraterrestrial materials, contributing to our understanding of solar system formation and the possibility of past life on Mars. Climate research in Antarctica has also revealed the continent's crucial role in global ocean circulation. The formation of cold, dense water masses around Antarctica drives deep ocean currents that transport nutrients and oxygen throughout the world's oceans. Changes in Antarctic ice sheet mass and ocean temperatures can affect these circulation patterns, with potential consequences for marine ecosystems and climate conditions worldwide. These modern discoveries continue to reshape our understanding of Antarctica's role in Earth's systems and its potential as an analog for extraterrestrial environments, making it one of the most scientifically valuable locations on our planet. The human story of Antarctic exploration represents one of the most remarkable chapters in the history of discovery, marked by extraordinary courage, devastating tragedies, and ultimately unprecedented international cooperation. From the first tentative approaches to the continent's icy shores to the establishment of permanent research stations, Antarctica's exploration history reflects humanity's drive to understand the unknown, even in the face of seemingly insurmountable challenges. The continent was the last to be discovered, with the first confirmed sightings occurring in 1820 by 3 separate expeditions. Russian explorer Fabian von Bellingshausen, British Royal Navy Captain Edward Bransfield, and American sealer Nathaniel Palmer each claimed to have seen the Antarctic landmass within days of each other. However, it would take another year before anyone set foot on the continent when American sealer John Davis made the first recorded landing on the Antarctic Peninsula in 1821. The period from roughly 1895 to 1917 is known as the heroic age of Antarctic exploration, characterized by national expeditions aimed at scientific discovery and geographic achievement. This era produced some of history's most famous polar explorers and most tragic tales of human endurance. The race to reach the South Pole became a defining moment of this period, culminating in Norwegian Roald Amundsen's successful expedition in December 1911, followed 5 weeks later by British explorer Robert Falcon Scott's team, who perished on their return journey. Scott's Terra Nova expedition, 1910-1913, exemplified both the scientific ambitions and human costs of early Antarctic exploration. Despite the tragic deaths of Scott and 4 companions, the expedition made significant scientific contributions, including the collection of geological specimens that provided some of the first evidence of Antarctica's connection to other southern hemisphere continents. The 35 pounds of geological samples that the team carried to the end, even as they faced starvation, demonstrated the priority they placed on scientific discovery. Ernest Shackleton's Endurance expedition, 1914-1917, became legendary not for reaching the South Pole, but for one of history's greatest survival stories. When their ship became trapped and eventually crushed by pack ice, Shackleton led his 27-man crew through nearly 2 years of survival on ice floes and barren islands, before mounting a desperate rescue mission across some of the world's most dangerous waters. Remarkably, every member of the expedition survived, a testament to Shackleton's leadership and the crew's resilience. These early expeditions relied on primitive technology and faced extraordinary hardships. Teams used wooden ships that were vulnerable to ice damage, primitive heating, and shelter systems, and limited communication capabilities that left them isolated from the outside world for months or years at a time. Transportation across the ice depended on dogs, ponies, and human hauling, making every mile a struggle against brutal weather conditions and treacherous terrain. The scientific legacy of the heroic age extended far beyond geographic achievement. Expeditions collected thousands of geological, biological, and meteorological specimens, mapped vast areas of previously unknown territory, and established the foundation for understanding Antarctica's role in global weather patterns. The detailed journals and photographs from these expeditions provided the first comprehensive documentation of Antarctic environments and wildlife. World War II marked a turning point in Antarctic exploration as military interests began to overlap with scientific curiosity. Several nations, including Germany, the United States, and Argentina, launched expeditions with both scientific and strategic objectives. Operation High Jump, the massive American naval expedition of 1946 to 1947, led by Admiral Richard Byrd, involved over 4,700 personnel and represented the largest Antarctic expedition in history. While officially focused on training and mapping, the operation's scale suggested broader geopolitical interests in the continent. The International Geophysical Year, IGY, of 1957-1958 transformed Antarctic exploration from national competition to international cooperation. 12 nations established over 50 research stations across the continent, sharing data and coordinating research efforts. The scientific discoveries made during IGY, including detailed mapping of the ice sheet and upper atmosphere research, demonstrated Antarctica's value as a natural laboratory and set the stage for continued international collaboration. The success of IGY cooperation led directly to one of the most remarkable diplomatic achievements of the Cold War era, the Antarctic Treaty, signed in Washington, D.C. on December 1, 1959. At the height of Cold War tensions, 12 nations agreed to set aside territorial claims and military interests to preserve Antarctica for peaceful scientific research. The treaty, which entered into force on June 23, 1961, established Antarctica as a scientific preserve and nuclear-free zone. The Antarctic Treaty's key provisions include a prohibition on military activities, nuclear testing, and nuclear waste disposal, freedom of scientific investigation, and free exchange of scientific information and personnel. Perhaps most importantly, the treaty froze all territorial claims, preventing conflicts over Antarctic resources while ensuring that no single nation could claim sovereignty over the continent. This governance without government model has proven remarkably successful, with no military conflicts occurring in Antarctica since the treaty's implementation. The treaty system has evolved over time through additional protocols and agreements. The 1991 Protocol on Environmental Protection, Madrid Protocol, designated Antarctica as a natural reserve devoted to peace and science and banned mining activities for at least 50 years. This protocol reflected growing environmental awareness and recognition of Antarctica's unique ecological value. Today, the Antarctic Treaty System includes 54 parties, representing about 2/3 of the world's population. 29 countries maintain consultative status, meaning they conduct substantial research activities in Antarctica and participate in decision-making processes. The system operates through annual Antarctic Treaty consultative meetings, where parties discuss scientific cooperation, environmental protection, and operational issues. Modern Antarctic operations bear little resemblance to the heroic age expeditions. Sophisticated logistics networks transport thousands of researchers and support personnel to Antarctica each year, supported by specialized aircraft, icebreaker ships, and advanced communication systems. Research stations provide comfortable living conditions with internet connectivity, fresh food, and recreational facilities, though the isolation and extreme environment still present significant challenges. The evolution from competitive national expeditions to cooperative international research represents one of diplomacy's greatest successes. The Antarctic Treaty demonstrated that even during periods of intense international tension, nations could work together for common scientific goals. This cooperation has enabled discoveries that would have been impossible for any single country to achieve alone, and has protected Antarctica from the conflicts that have affected other regions of the world. The treaty's success provides a model for international cooperation in other frontier areas, including outer space and the deep ocean, and continues to govern human activity in one of Earth's last pristine wilderness areas. Antarctica serves as Earth's most sensitive barometer for climate change, where shifts in global temperature and atmospheric composition manifest in dramatic and measurable ways. The continent's role in the global climate system extends far beyond its massive ice sheets. It functions as a crucial component of ocean circulation, atmospheric dynamics, and the planetary energy balance. Understanding these processes has become increasingly urgent as researchers document accelerating changes that could reshape coastlines worldwide. The West Antarctic ice sheet, containing enough water to raise global sea levels by approximately 3.3 meters, has become a focal point of climate research due to its vulnerability to warming ocean temperatures. Unlike East Antarctica, where the ice rests primarily on bedrock above sea level, much of West Antarctica's ice sits on bedrock below sea level, making it susceptible to marine ice sheet instability. When warm ocean water penetrates beneath the ice sheet, it can trigger rapid retreat that continues far inland. Recent satellite observations have documented alarming changes in West Antarctic glaciers. The Pine Island and Thwaites glaciers, two of Antarctica's largest ice streams, have accelerated their flow into the ocean dramatically over the past several decades. The Thwaites Glacier, often called the Doomsday Glacier due to its potential for rapid collapse, has been retreating at an accelerating rate. Its grounding line, the point where the glacier lifts off the seafloor and begins floating, has retreated more than 14 kilometers since the late 1990s. Temperature records from Antarctic research stations provide direct evidence of regional warming trends. The Antarctic Peninsula has experienced some of the most rapid warming on Earth, with average temperatures increasing by nearly 3 degrees over the past 50 years. This warming has triggered the collapse of several major ice shelves, including the Larsen B ice shelf, which disintegrated over just a few weeks in 2002, releasing more than 3,000 square kilometers of ice that had been stable for thousands of years. The loss of ice shelves has implications extending far beyond the immediate area. These floating ice platforms serve as natural dams, slowing the flow of land-based ice into the ocean. When ice shelves collapse or thin significantly, the glaciers behind them accelerate, contributing directly to sea level rise. The phenomenon creates a positive feedback loop. As ice shelves thin due to warming ocean temperatures, they become more vulnerable to complete collapse, which further accelerates ice loss. Sea ice around Antarctica exhibits complex patterns that reflect the continent's unique geography and oceanography. Unlike Arctic sea ice, which shows a clear declining trend, Antarctic sea ice extent has shown high year-to-year variability, with some regions experiencing increases while others show decreases. The Ross Sea region has seen expanding sea ice coverage in some years, while the Amundsen and Bellingshausen seas have experienced significant decreases. These regional variations reflect the complex interaction between changing wind patterns, ocean temperatures, and ice sheet dynamics. The Southern Ocean surrounding Antarctica plays a crucial role in global climate regulation through its capacity to absorb carbon dioxide and heat from the atmosphere. This ocean region accounts for approximately 40% of global carbon dioxide absorption, despite representing only 20% of the world's ocean area. The cold, turbulent waters efficiently mix atmospheric carbon dioxide into deep ocean layers, where it remains sequestered for decades to centuries. However, as the Southern Ocean warms, its capacity to absorb carbon dioxide may diminish, potentially accelerating atmospheric carbon dioxide accumulation. Changes in Antarctic ice mass have accelerated significantly since the 1990s. Satellite gravimetry missions, including the Gravity Recovery and Climate Experiment, GRACE, have provided precise measurements of ice mass changes across the continent. These data show that Antarctica has lost approximately 150 billion tons of ice annually since 2002, with losses accelerating in recent years. The majority of this ice loss comes from West Antarctica and the Antarctic Peninsula, while East Antarctica has remained relatively stable or shown slight gains in some regions. The atmospheric circulation patterns around Antarctica, particularly the Southern Annular Mode, SAM, significantly influence the continent's climate and its connection to global weather systems. The SAM represents the north-south movement of the westerly wind belt that encircles Antarctica. When the SAM is in its positive phase, the westerly winds strengthen and contract toward Antarctica, leading to cooling over much of the continent but warming along the Antarctic Peninsula. Climate models suggest that human activities, particularly ozone depletion and greenhouse gas increases, have influenced SAM patterns. Ozone depletion over Antarctica, discovered in the 1980s, created a dramatic example of how human activities could affect even the most remote regions of the planet. The Antarctic ozone hole, which forms each spring due to the interaction between polar stratospheric clouds and chlorofluorocarbon pollution, has influenced temperature and wind patterns across the southern hemisphere. While the Montreal Protocol has successfully reduced ozone-depleting substances, the ozone hole continues to affect Antarctic climate and will likely persist for several more decades. Precipitation patterns across Antarctica are changing in complex ways that vary significantly by region. Some areas of East Antarctica have experienced increased snowfall, which partially offsets ice losses elsewhere on the continent. However, warmer temperatures have also increased the frequency of rainfall events along the Antarctic Peninsula and coastal regions, where liquid precipitation can accelerate ice melting and weaken ice shelf structure. The concept of tipping points has become central to discussions about Antarctic climate change. Scientists have identified several potential thresholds beyond which changes might become irreversible or self-reinforcing. The collapse of the West Antarctic ice sheet represents one such potential tipping point, where marine ice sheet instability could lead to continued retreat regardless of future climate conditions. Other potential tipping points include the complete loss of summer sea ice and major changes in Southern Ocean circulation patterns. Ice core research continues to provide crucial context for understanding current changes by revealing how Antarctic climate has varied naturally over thousands of years. These records show that current rates of change are unprecedented in the geological record, with atmospheric carbon dioxide concentrations and temperature increases occurring much more rapidly than during natural climate transitions. The ice core record also reveals that the Antarctic ice sheet can respond rapidly to climate changes, with major reorganizations occurring over decades rather than centuries. Research into Antarctic climate change faces unique challenges due to the continent's extreme environment and limited observational network. Automated weather stations provide year-round data from remote locations, while satellite observations offer comprehensive coverage of ice sheet changes, sea ice extent, and atmospheric conditions. However, the short duration of satellite records and sparse ground-based observations in some regions create uncertainties in understanding long-term trends and natural variability. The implications of Antarctic climate change extend far beyond the continent itself, affecting global sea levels, ocean circulation patterns, and regional weather systems throughout the southern hemisphere. Life in Antarctica exists in forms and places that challenge fundamental assumptions about the requirements for biological survival. Despite conditions that seem utterly hostile to life, temperatures that regularly plummet below 40 months of complete darkness and landscapes drier than most deserts, Antarctica hosts a remarkable diversity of organisms that have evolved extraordinary adaptations to thrive in one of Earth's most extreme environments. The discovery of extensive microbial communities in Antarctica's permanently frozen soils, known as permafrost, has revolutionized understanding of life's persistence in extreme cold. These microscopic organisms, including bacteria, fungi, and archaea, remain metabolically active at temperatures well below freezing by producing antifreeze proteins and specialized enzymes that function efficiently in cold conditions. Some microbial communities in the McMurdo Dry Valleys have been radiocarbon dated to over 100,000 years old, suggesting they have survived multiple ice ages while maintaining viable populations. Antarctic microbial mats represent some of the most ancient forms of life on Earth, similar to communities that dominated the planet billions of years ago. These layered structures, composed of different species of cyanobacteria and other microorganisms, create their own microenvironments that can be several degrees warmer than surrounding conditions. In lakes throughout the McMurdo Dry Valleys, these mats form intricate patterns on lake bottoms, creating underwater gardens of unexpected beauty and complexity. The recent exploration of subglacial environments has unveiled entirely new ecosystems that have evolved in isolation for millions of years. Lake Whillans, located beneath 800 meters of West Antarctic ice, contains a thriving microbial community that derives energy from chemical reactions with minerals in the underlying sediment. These chemosynthetic organisms represent a completely independent food web that has never relied on sunlight, providing insights into how life might exist on ice-covered moons like Europa or Enceladus. Bloodfalls in the McMurdo Dry Valleys provides a dramatic example of life persisting in conditions that initially appear sterile. The iron-rich water that creates the fall's distinctive red color originates from a subglacial reservoir that has been sealed from the atmosphere for over 1 million years. Within this ancient water, researchers have discovered microorganisms that use iron and sulfur compounds as energy sources, representing one of the few known ecosystems on Earth that operates completely independently of photosynthesis. Marine ecosystems around Antarctica demonstrate remarkable productivity during the brief summer season when continuous daylight fuels massive phytoplankton blooms. Antarctic krill, small crustaceans no larger than a human finger, form swarms that can extend for hundreds of kilometers and contain billions of individuals. These krill aggregations support complex food webs that include 6 species of seals, numerous whale species, and millions of seabirds, creating some of the most spectacular wildlife displays on Earth. Emperor penguins represent perhaps the most iconic example of Antarctic adaptation, with breeding behaviors that seem to defy biological logic. These remarkable birds breed during the Antarctic winter, when temperatures drop to 40 degrees Celsius and howling winds create whiteout conditions. Males incubate eggs on their feet for over 2 months, while females travel hundreds of kilometers to feed in the ocean, returning with food for newly hatched chicks, just as the males reach the limits of their energy reserves. The discovery of thriving ecosystems beneath Antarctic ice shelves has overturned assumptions about life in permanently dark, cold environments. Researchers drilling through the Ross Ice Shelf have found diverse communities of fish, crustaceans, and other marine organisms living in waters that never see sunlight. These creatures survive by feeding on organic matter that drifts in from distant ocean regions, creating food webs that stretch across thousands of kilometers of ocean. Antarctic notothenoid fish represent one of evolution's most remarkable success stories, having diversified into over 120 species that dominate Southern Ocean fish communities. These fish produce antifreeze glycoproteins that prevent ice crystals from forming in their blood and body fluids, allowing them to remain active in waters that would freeze most other fish species solid. Some species have even lost their ability to produce red blood cells, instead relying on dissolved oxygen in their blood plasma, an adaptation that works only in the oxygen-rich cold waters of the Southern Ocean. Terrestrial arthropods in Antarctica, though limited in diversity, demonstrate extraordinary resilience to extreme conditions. The Antarctic midge, Belgica antarctica, is the continent's only native insect and can survive being completely frozen solid for months at a time. These tiny flies have eliminated flight capability to conserve energy and can lose up to 70% of their body water without dying. Their larvae can withstand temperatures below 15 degrees C and complete dehydration, entering a state called anhydrobiosis, where all metabolic processes cease until conditions improve. Lichens and mosses dominate Antarctica's limited terrestrial plant communities, forming complex relationships that allow survival in conditions that would kill most vegetation. Some lichen species grow so slowly that individual specimens may be thousands of years old, representing some of the oldest living organisms on Earth. These composite organisms, formed by partnerships between fungi and algae or cyanobacteria, can photosynthesize at temperatures near freezing and survive complete desiccation during winter months. The study of extremophile organisms in Antarctica has provided crucial insights for astrobiology research. NASA and other space agencies use Antarctic environments as analogues for conditions that might exist on Mars, Europa, and other celestial bodies where life might potentially exist. The discovery that life can persist in Antarctica's most extreme environments, in the absence of sunlight, liquid water, or moderate temperatures, expands the potential habitable zone for life throughout the universe. Invasive species represent a growing threat to Antarctica's unique ecosystems as human activity increases and climate change alters environmental conditions. Non-native organisms arrive through various pathways, attached to ships and aircraft, in food supplies, on equipment, and even on researchers' clothing and gear. A single seed or insect that establishes a breeding population could potentially disrupt ecosystems that have evolved in isolation for millions of years. The bluegrass Poa annua, accidentally introduced to the Antarctic peninsula, has begun spreading rapidly in areas where temperatures have risen sufficiently to support its growth. This seemingly innocuous grass could potentially outcompete native moss and lichen communities, fundamentally altering the structure of terrestrial ecosystems. Similarly, the introduction of non-native marine species through ship ballast water poses risks to Southern Ocean communities that have no evolutionary experience with such organisms. Conservation efforts in Antarctica focus heavily on prevention rather than control, since removing invasive species from such remote and harsh environments is often impossible once they become established. Strict biosecurity protocols require thorough cleaning and inspection of all equipment, clothing, and supplies before transport to Antarctica. Research stations maintain quarantine facilities and sterilization equipment to prevent accidental introductions, climate change is creating new opportunities for both native and invasive species to colonize previously uninhabitable areas of Antarctica. As temperatures warm and ice-free areas expand, species from subantarctic islands and southern continents may naturally disperse to Antarctica, while existing Antarctic species may expand their ranges into newly available habitats. Understanding these natural colonization processes helps researchers distinguish between natural range expansions and human-mediated invasions. The unique evolutionary history of Antarctic organisms provides insights into speciation, adaptation, and survival strategies under extreme conditions. Many Antarctic species show signs of recent rapid evolution, having colonized the continent as it cooled and became isolated. The limited number of founding species that successfully established populations in Antarctica have often undergone adaptive radiation, evolving into multiple specialized forms to exploit different ecological niches. Marine protected areas around Antarctica aim to preserve critical feeding and breeding habitats while allowing sustainable scientific research. The Ross Sea Marine Protected Area, established in 2017, covers 1.55 million square kilometers and represents one of the world's largest protected areas. These conservation measures recognize that Antarctic ecosystems, while appearing robust in their harsh environment, may be particularly vulnerable to human impacts due to their isolation and the specialized nature of their component species. Research into Antarctic biology continues to reveal new species and ecological relationships. Recent expeditions have discovered previously unknown species of bacteria, invertebrates, and even fish in various Antarctic environments. Each discovery adds to our understanding of life's limits and possibilities, while emphasizing how much remains unknown about one of Earth's most extreme and inaccessible ecosystems. Antarctica stands at a critical juncture where the forces of climate change, increasing human activity, and growing scientific understanding converge to create both unprecedented opportunities and existential challenges. The continent's future will be shaped by decisions made in the coming decades regarding environmental protection, international cooperation, and the balance between scientific research and conservation priorities. The most pressing challenge facing Antarctica is the accelerating pace of climate change and its cascading effects throughout the continent's interconnected systems. Current climate models project that even under moderate warming scenarios, significant portions of the West Antarctic ice sheet may be committed to irreversible retreat. This process, once initiated, could continue for centuries, regardless of future emission reductions, potentially contributing 3 to 4 meters to global sea level rise and fundamentally altering coastlines worldwide. The concept of irreversible tipping points has become central to Antarctic climate research, as scientists work to identify critical thresholds beyond which changes become self-sustaining. The marine ice sheet instability, affecting glaciers like Thwaites and Pine Island, may represent such a tipping point, where warm ocean water penetration triggers unstoppable retreat. Understanding these thresholds is crucial for global climate policy, as they define the boundaries of what remains possible through mitigation efforts. Tourism in Antarctica has grown exponentially, from fewer than 2,000 visitors annually in the 1990s to over 70,000 in recent years before the COVID-19 pandemic. While tourism provides economic incentives for conservation and public education about Antarctic environments, it also presents significant environmental challenges. Ship traffic increases the risk of introducing invasive species, fuel spills, and physical disturbance to wildlife. The infrastructure required to support tourism operations can fragment sensitive habitats and alter local ecosystems. The management of Antarctic tourism requires balancing public access with environmental protection, Current regulations limit the size of tour groups, restrict access to certain areas, and require comprehensive environmental impact assessments. However, as tourism demand continues to grow and becomes more accessible through improved transportation technology, maintaining these protections while allowing meaningful experiences becomes increasingly challenging. Scientific research in Antarctica faces evolving challenges related to logistics, funding, and environmental impact. The cost of maintaining research stations and transporting personnel and equipment to Antarctica continues to rise, while funding agencies face competing priorities for limited resources. Climate change is also affecting research operations, as changing ice conditions alter transportation routes and facility requirements. The environmental impact of research activities themselves has become a growing concern. Research stations generate waste, consume energy, and require regular resupply flights that produce greenhouse gas emissions. Some research activities, such as ice drilling and wildlife studies, can potentially disturb the very systems they aim to understand. Balancing scientific knowledge needs with environmental protection requires ongoing evaluation of research priorities and methodologies. International cooperation remains the foundation of Antarctic governance, but faces new stresses as geopolitical tensions increase and resource pressures grow. The Antarctic Treaty System has successfully prevented territorial conflicts for over 6 decades, but questions about mineral resources, fishing rights, and strategic interests continue to create underlying tensions. Climate change may expose previously inaccessible resources while simultaneously making territorial claims more relevant. The potential for resource extraction in Antarctica, currently prohibited under the Madrid Protocol, represents a long-term governance challenge. As global demand for minerals increases and extraction technologies improve, pressure to reconsider mining restrictions may intensify. The 50-year prohibition on mining expires in 2048, requiring consensus among treaty parties to extend the ban. Maintaining the current environmental protections will require sustained international commitment and potentially new governance mechanisms. Emerging technologies offer both opportunities and challenges for Antarctic research and conservation. Autonomous research platforms can collect data from previously inaccessible locations while reducing human environmental impact. Satellite monitoring provides comprehensive coverage of environmental changes across the continent. However, these technologies also raise questions about data ownership, privacy, and equitable access to information. The development of space exploration technologies creates new connections between Antarctic research and broader human endeavors. Antarctica's extreme environments provide testing grounds for equipment and procedures that may be used on Mars or other celestial bodies. The psychological and logistical challenges of Antarctic research offer insights into long-duration space missions. These connections may provide new justifications for Antarctic research funding while creating additional pressures on pristine environments. Climate adaptation strategies for Antarctica must address both mitigation and adaptation approaches. While global emission reductions remain the most important long-term strategy, some changes are already inevitable due to past emissions. Adaptation approaches might include assisted migration of threatened species, restoration of degraded habitats, and enhanced protection of climate refugia where conditions remain suitable for native species. The role of Antarctica in global climate regulation extends beyond ice sheet contributions to sea level rise. The Southern Ocean's capacity to absorb carbon dioxide and heat affects global climate patterns, while Antarctic ice influences ocean circulation patterns worldwide. Changes in these systems could trigger additional climate feedbacks that amplify warming trends globally, making Antarctic research crucial for understanding future climate scenarios. Education and public engagement represent critical components of Antarctica's future as public support drives political will for environmental protection and research funding. The continent's dramatic landscapes and charismatic wildlife provide powerful symbols for environmental awareness, while its role in global climate systems demonstrates the interconnectedness of Earth's systems. Effective communication about Antarctic science and conservation challenges requires balancing scientific accuracy with accessible storytelling. The next generation of Antarctic researchers will inherit both unprecedented technological capabilities and increasingly urgent environmental challenges. Training programs must prepare scientists to work across disciplines, communicate with diverse audiences, and navigate complex ethical considerations related to research in pristine environments. International exchange programs and collaborative research initiatives will be essential for maintaining the cooperative spirit that has characterized Antarctic research. Looking toward 2048, when the Madrid Protocol's mining prohibition comes up for review, the international community will face critical decisions about Antarctica's future. The choices made in the coming decades will determine whether Antarctica remains primarily a scientific preserve and environmental indicator, or whether resource extraction and strategic competition reshape the continent's role in human affairs. The ultimate significance of Antarctica may lie not in what it contains, but in what it represents. Humanity's capacity for international cooperation, environmental stewardship, and scientific discovery in the face of extreme challenges. The continent serves as both a laboratory for understanding Earth's systems and a testing ground for our ability to protect irreplaceable natural environments. The decisions made about Antarctica's future will reflect broader choices about humanity's relationship with the natural world and our commitment to preserving Earth's remaining wilderness areas for future generations.